the next application of this? So I'm going to have two different organic structures. So this one is what we call N-butane. N just means that it's all in a line and there's nothing branching off of it. But prefix means 4. Okay? So what I have here is I have 4 carbon atoms, each one surrounded by either the ends have 3 hydrogens on them. If you were to draw this structure, so you'd have carbon, hydrogen, hydrogen, carbon, boom, boom, carbon, boom, boom, another carbon, hydrogen, hydrogen, hydrogen. Okay? So butene's 4, there's 4 of them. Jordan, what type of hybridization is every carbon atom undergoing? Beautiful. Okay? All of those are undergoing sp3 hybridization. There's this nice little chain. Here it is. Okay? Now, in contrast to that, we're going to have a different structure called 2-methylpropane. So, not to ruin the surprise of organic chemistry, but what the 2 represents is the carbon atom to which we have attached a methyl group. A methyl group is a fancy way of saying it's a carbon with 3 hydrogens attached to it. So alcohol groups are OHs, methyl groups are CH3s. No, I'm not going to expect you to know that for the test. Okay? Just a general background kind of knowledge kind of thing. So this one looks like this. Okay? So the reason that we call it 2-methyl is because the second carbon N has a methyl group attached to it. Okay? So what's common is this. They both contain the same number of carbon atoms. Okay? They both contain 4 carbon atoms. But the difference is that this carbon atom is stuck up here as a methyl group, whereas these carbon atoms are all in a line. Okay? Do any of these have hydrogen bonding?
No way.
No way. Why?
No.
They have no nitrogen, oxygen, or fluorine. They have hydrogen, but they don't have the nitrogen, oxygen, or fluorine. Now, here's the million-dollar question. They both contain 4 carbons. That's the same. They both contain 4 carbons. sp3 hybridization, still the same. But the question being is that why does N-butane have a boiling point of negative 0.5 degrees Celsius, but the methylpropane has a boiling point of minus 12 degrees Celsius? That's the question. So, what do you got?
The butane is linear, and the other one is more volatile.
Okay, so what?
So it's like the polarizability thing, where it's like this one's longer, so more of it can go like over there. Whereas the littler
force and distance, like the greater distance less.
You've spoken wisely, Adam. So here's the story. So this is a non-technical term, but this is spiking. Okay? So imagine that you're going to try and bring 2 of these together. Okay? So if you try and bring these together, it's kind of like a triangle, if you generalize this being like the shape of a triangle. Okay? Whereas this is more linear. So remember, if you're going to induce this dipole moment, these have to collide, and what you do is you create a disturbance in the arrangement of the chihuahuas. So if I bring these together, the chihuahuas here don't like the chihuahuas there, and they move. Oh, that creates a temporary dipole moment. So because this is linear, you're going to, when these run into each other, there's going to be more surface area. So because that has more surface area, that's easier to induce that dipole moment because there's going to be more area that's in contact. So the London dispersion forces in terms of electron clouds are about the same. Okay? That's about the same. Neither one of them really has a dipole moment, because there isn't like an oxygen or a chlorine group or something like that attached to it. Okay? That's about the same. So you have to explain what the boiling point is happening. So remember, the boiling point is a measure of stickiness. Now, at room temperature, in what phase would both of these exist?
Yeah.
Gases or liquids?
Yeah.
Gases. Why?
Or way above the boiling point.
Yeah, we're at 20 degrees Celsius. So neither one of these would exist as liquids. You'd have to cool them down. But here's the other side of this. Let's say that I have a container that has the N-butane in it, and it also has the 2-methylpropane in it. Okay? So I have a container, and it has equal number of moles of each one. Okay? So let's make it easy. Let's say each one has a half mole of each. Okay? And then what's going to happen is that I'm going to begin to cool this down. Okay? I'm going to begin to drop that temperature. So here's the other side of it. If I cool it down, which one would condense first? The N-butane or the 2-methylpropane?
Control back up.
Yeah. Well, I need to.
So if I cool it down, okay, I'm going to put this into the refrigerator. Freezer in this case, because that's the below zero. I'm going to begin to cool this down. Which one will condense into a liquid first? The N-butane or the 2-methylpropane? N-butane. Why?
Has a higher boiling.
Yeah. So the N-butane is more sticky. So as you cool it down, okay, the N-butane would condense into a liquid first. So because of the fact that it has the higher boiling point. Now, if you had them as both liquids, okay, if you mix them together as liquids and like say they're at minus 14, the other side of it though would happen. If they were both liquids, these are as gases. If I have them both as liquids at minus 14 degrees Celsius, okay, minus 14 degrees Celsius, and I'm going to warm it up, which one will boil first? The 2-methylpropane or the N-butane?
2-methyl.
The 2-methyl will boil first. So when you see those bubbles form, that's going that 2-methylpropane is going to boil first because it has the lower boiling point. So that's what you need to think through. Okay, what's happening with boiling point, and that's a reflection of how sticky it is, which I know is a non-scientific term, but it works. So here's the big ideas that you're going to need for tomorrow. Okay, your hybridizations, SP, SP2, SP3. Okay, technically there's some other ones like DSP2 and stuff like that. I'm not going to ask you about. Okay, the only things I'm going to ask you about are SP, SP2, SP3. Make sure that you can do stoic with gas laws. Okay, like on the assignment that I just gave back. All right, where I'm going to give you information. I might say, hey, you know, here's a reaction. It might have like 7 grams of hydrogen at a certain amount of pressure and temperature, and then I'm going to have 0.3 moles of hydrogen gas that's going, or oxygen gas that's going to react with, and then say, hey, what's the limiting reactant? So if you look at PV equals nRT, right? What's the one situation where 1 mole has a volume of 22.4 liters? It's the only time. Yes, I would have to specifically tell you that it's under standard temperature and pressure. That is the only time you can let 1 mole occupy 22.4 liters. Now, in gas laws, What's the temperature for standard conditions of gas law?
298 Kelvin.
No,
Gas, 0.
Celsius,
Yeah.
273 Kelvin.
which is 270
Well,
Kelvin.
I thought that was pretty obvious.
Okay? So, in gas laws, standard temperature is 0 degrees Celsius.
Oh, that's what I meant.
That's not what you said.
I know. My bad.
You said
Can't
298.
teach an old dog new tricks.
Huh?
Now, so gas laws, temperature is 0, okay, Celsius, which is 273 Kelvin. For solution, standard temperature is
25 degrees Celsius.
25 degrees Celsius, which is,
I'm locked in.
there you go. You just had the gas law one instead of the other one. Okay. Let me see what else. Those are going to be like the big things. So on the review, and yes, you have to read it.
Berg, is this going to be more like a quiz because it's so short?
No, it's going to be, here's my fear. Okay? Here's my fear. You're going to think, this is just a quiz. I really don't need to study.
I need to study.
More than one student has come in with that attitude and got their world rocked. Okay? I'm just telling you, if your mind is set as like, this is just going to be like a quiz, I really don't need to study, you might reconsider that thought process. Okay? I'm just saying. So, on the review, yes, you're getting the blank, and yes, you're getting the answer key. So, on this first one, this is, I promise you there's going to be a question like this. I promise you. It's the one where you have like the two vessels that are connected. You have like one gas on one side and one gas on the other. Yes, like that. Okay? Promise you there's going to be one like that. And I promise you, I'm going to tell you I want it in a specific unit, like torrs, atmosphere, something like that. Make sure you read that part of it. Yes.
Are we giving like conversion?
760 torr per 1.
Yes.
I don't remember.
I will give you the conversions. Okay, I promise you. When you get to question number 8, you have two different molecules, and I give you their dipole moments. So dipole moments are these weird units. So like the first one that you're going to have is 3.9 D, and the second one is 1.62 D. The bigger the number is, that's just a reflection of the bigger dipole moment. Okay? So dipole moments really don't have a measurement. That's why we put them as D. So it's a relative value. It isn't like, oh, it's voltage or it's amperage or something like that. Okay? It's just a number. So that's what that's talking about. In terms of trends on the periodic table, okay, here's your basic periodic table. There's 3 trends you should know. Electronegativity. So remember, electronegativity is the willingness to basically pull in electrons from another atom or another group of atoms, another molecule. Okay? So this would be like a measure of who is most willing to form a bond with other people to get 8 game pieces. So the extremes are always the halogens and the noble gases and the alkali metals. So of the 3 alkali metals, the halogens or the noble gases, which one of those 3 are going to have the highest electronegativity? The halogens. Why?
They need one more.
They have 7 game pieces, they need 1 more. Okay? They have 7 goats, they need 1 more goat. I don't care how you understand it. What about the noble gases?
They're content. They're content.
They have no electronegativity, they gain nothing. In terms of formal charge, I will not expect you to do the calculations of formal charge. But what I will give you a situation is go, hey, you have 2 situations. one in which carbon has a formal charge of -1, and another structure where nitrogen has the formal charge of -1. Which one is going to be more favored? This one where the structure has, where the carbon has the charge of -1, or the nitrogen has the formal charge of -1? Huh? Why?
More electrons.
One more.
So, with formal charge, the preferred structure is the one that has the negative charge associated with a higher electronegativity. So if you have carbon and nitrogen, you just have to realize, oh, nitrogen is further right, or that has a higher electronegativity.
Real quick, what's formal charge?
Huh?
What's formal charge?
Formal charge is just a way of assigning a numeric value to certain atoms within it. I'm not going to expect you to calculate it. I will give you the formal charge.
Okay.
Okay? Don't calculate it. I will give the number to you. Okay. Now, electron affinity is referring to its willingness to hold on to its own kind of electrons. Okay? So that electron affinity kind of follows the same pattern. Alkali metals, they only have one gain piece, they really don't care. Halogens really want to hold on to theirs. The noble gases have the highest electron affinity because of the fact that they have all 8 gain pieces. First ionization energy is a similar type thought process. First ionization energy is how easy it is to create, if you're in AP physics, the photon electric effect. Which one is easiest to take the electrons from it? Now, Adam has 1, Mora has 7, Jordan has 8 gain pieces, right? I want to take a gain piece from one of them, but I don't have it in me to fight.
There's one.
Which one am I going to, who am I going to take it from? Adam. Why?
It's like taking candy from a baby.
I don't really care about it.
Yeah, he only has one. It's like, hey, Adam, can I have a gain piece? Sure, I don't care. Jordan would say, Mr. Burkamp, respectfully, you're going to have to fight. Okay? Because she has all 8 gain pieces. So, noble gases have the highest first ionization energy because they have the winning pieces. Now, as you go down a group, what happens to first ionization energy?
Decreases
Why?
because the electron cloud gets bigger.
Yeah, remember
Coulomb's law.
Coulombic forces. So the farther the electrons are from the nucleus, the easier they are to take those away. Keep that in mind.
Because it's over d squared.
Huh?
Because it's over d
Oh, it's over d squared. When you get to question number 15, promise you there's going to be a question like 15. You're taking hydrogen and nitrogen and you're reacting it to produce ammonia. And then you're going to figure out the total pressure once the reaction is completed. So remember, you're going to have some nitrogen, you're going to have some hydrogen, that's going to react to produce ammonia. I've given you, once you read number 15, I've given you information about the moles of hydrogen and the moles of nitrogen. Since you have information about both reactants, what type of reaction is it? Limiting reactant problem. Okay? I promise you there's going to be one like 15 on the test tomorrow. Mark my word. Okay? I promise you there's going to be one like 15. I promise you. Okay? Just saying. All right, Mara, shut that down.
Well,
All